We kind of did go over general arrangement, but we'll go into this a little further and tell you more about design drivers. So one of the requirements we were talking about was the placement of things, their orientation. So that falls under the category of geometry. So let's delve a little deeper. For each subsystem, there are geometrical considerations for the way the structures should lay out all of the different components. So for a payload, you're gonna drill this into your brain. A lot of them require unoccluded field of view, but also you have to consider the thermal deformation in critical payload components. This is important for the James Webb Space Telescope, for example, where the optical components and the detectors are thermally sensitive. So when you're thinking about where to place them, you want to place it, say, away from the components that are generating the most amount of heat. That could be like the propulsion subsystem or the power generation subsystem. And then for electromagnetic interference, if you have a magnetometer that is your payload, again, you want to place it far away from things that generate its own magnetic field, which would disturb your science measurements. For your structures and mechanisms subsystem, you want to make sure that all the components actually feasibly fit together, that when you're creating your CAD, that these geometries, these volumes don't intersect with each other. It should be that the software will give you an automatic warning if something like that happens, but just pay attention to that when you're designing a good structure system. You may also have to account for vibration isolation for some components. I know that some dynamic sensors, like an IMU, are sensitive to shock and vibration, or payload components for that matter. So you may want to build that in. For thermal control, the spacecraft structures, depending on the material, have different thermal conductivity. So you can either facilitate conduction or insulation based off of your spacecraft structure. And then we'll talk about this more in the thermal control subsystem, but the structure subsystem may pair well with the thermal control system if you can use the structure as a passive way of like shunting or transferring heat across brackets or structures. But you can also thermally isolate something if you choose to, say, use plastic in your brackets to stop or mitigate heat flow. For power, you want to think about the way that boards are connected, and that's called harnessing, the cables between different boards. So the structures lead has to think about where these wires are going to be routed through. If you don't leave any kind of room for wiring to like flow through the structure, then it's an infeasible design. So there's a little bit of like nuance to the way you envision the layout of the different boards. And then like we're talking about, this placement of the battery, you could insulate that if the battery is thermally sensitive. For telemetry and control, or for communications, we were talking about how the antenna wants an unoccluded field of view when it's transmitting back to Earth. For command and data handling, we're talking about radiation shielding, so typically embedded in the center of the spacecraft. And then for sensors and actuators, the attitude determination and control system cares about the way the sensors and actuators are mounted in its orientation within the spacecraft. So you'll see here that there are these coils of wire. We are designing one. You can actually ask Kalai about torque coils that we're trying to embed behind solar panels. So those orientations matter. the sun sensor orientation matters, and so does the star tracker's orientation. Another thing that's important for attitude determination and control is that distribution of mass. Not only do you want that center of mass to be close to the geometric center of the spacecraft, but you also want to minimize off-diagonal moments of inertia. And we can cover that in the attitude determination and control subsystem mathematically, but essentially these off-diagonal moments of inertia complicates the way that spacecraft spin. Instead of having motion that's like tucking, like a somersault, imagine if you have an off axis, then you would start to skew off from that axis of rotation. So you would get maybe a little bit of wobble as you're tucking. So that is typically not desired because it's not as predictable. And then finally, we were talking about propulsion. The direction of thrusters matters. The placement of the propellant exhaust should probably be away from the payload if you can avoid it. Whew, okay. And I think I talked about this one enough, so I'm gonna skip it. Okay, so we were talking about critical loads earlier. And we care about critical loads because we care about the structural integrity of our spacecraft. So what are the different kind of loads that a structure can experience? This is essentially a statics 101 in the field of mechanical engineering. If you're in mechanical engineering, sorry, bear with me, but I just want to give the most basic foundation of the different loads or forces that can occur within a spacecraft. Loads are important because with a big enough load, a structure can fail. So there are static loads where you're just applying a constant load on a structure. There are quasi-static loads. So there are things called dynamic loads where the load is being applied differently over time. One of those is a cyclic load where your minimum and your maximum are pretty steady, but you transition between those kind of loads. There's an impact load where maybe you can think about if your spacecraft were dropped or it deflects and hits some other spacecraft, or a micrometeoroid hits your wall. Those are impacts. Normal loads are loads associated with direction. So tension is axially away, compression is axially in. Shear loads are where loads are perpendicular to your structure. Torsional loads are associated with twisting. Bending loads are associated with, it's like a shear load, but the resultant action is not shearing, but is instead bending. A buckling load is like a normal load, but also the resultant consequence is this like bending or buckling motion. And then finally, there's something called a vibrational load, which is not like any of these where you have a force. Vibrational loads are based off of acceleration profiles associated with frequencies. Okay. So sources of loads. Loads can happen at many stages of the spacecraft design process. For manufacturing and integration, there are thermal stressors and joint stressors due to tightening bolts. So here I have a video of a weld in action. So you'll see that at the beginning, the hot molten metal that is being used to weld two things together doesn't have much stress associated with it, but as it cools, you'll see a high amount of stress at that joint. Yep, so dark blue is minimal loading, and then red is high loading. So you see the parts that are being connected at the outer edges, not much stress. But as you are cooling, the steady state is for that joint to accumulate some stress that, could contribute to a failure. And then here is a picture of a bolt. And you have to tighten bolts, right? But that does apply some stress to the threads as you're tightening and joining this joint together. There are protocol for how tight you need to screw bolts into a joint. You can use torque wrenches for that. But the ultimate consequence is that with that preload, you're contributing to stress on this fastener, and with additional stress on that joint could contribute to a failure, which is something you want to avoid. Okay, so I got questions about, don't most welds cause some kind of warping of the metal because of the heat? So mechanical stress is induced when metal is bent, formed, or stamped. More destructive, however, is the thermal stress created when metal is cut, welded, cast, drilled, or quenched as a result of a sharp drop in its temperature. For example, when welding, air quenches the metal as you move away from the line of work. This zone is known as a heat-affected zone. During this sharp temperature drop, both the metal and the HAZ are affected. This results in potential cracking or distortion over time. In the process of torquing bolts, we apply a preload to the joint. A preloaded joint is closer to failure depending on the amount of preload. And then a follow-up question is, which is better in a CubeSat, welding or using mechanical fasteners? So for a good weld job, welding is stronger than bolts, typically across the board. But there are other factors associated with a weld that makes it inconvenient or costly. Historically, we weren't able to make bolts strong enough for high load bearing or high vibration applications. Today, we are seeing more frequent use of technology like lock bolts as we're able to make materials stronger. Although welding is a sure and true way to secure a joint, welding is very time-consuming, nearly impossible to undo, can damage critical surfaces, and requires personnel time to inspect the quality of weld, both costly and time-consuming. For the purposes of CubeSats, the loads are not very high, so fasteners are more than capable of supporting those kind of loads. Other loads are associated with transport and handling. And then I have impact or shock listed here as a load. And you'll see that in actual missions as well, like the Orion spacecraft. So impact or shock profiles look like so, where there is a huge spike in acceleration experienced by a spacecraft due to the impact. I talked a little bit earlier about components that are sensitive to impact or shock, like sensors. So you do want to maybe vibrationally isolate those components, and also handle your CubeSat with care. Hopefully you don't want to ruin a mission because of some clumsiness in the process of the development. But you know what? Some spacecraft are designed to withstand shock, like the Orion crewed capsule. A question is, will the CubeSat survive being hit by space debris? And the answer is, it depends by the size of the space debris. I can't imagine that centimeter-sized space debris that would probably puncture the spacecraft, given that the CubeSat walls are very thin. So it'd have to be pretty small space debris and not going at very high velocity for the CubeSat to survive. other sources of loads, launch and packaging. So hopefully you recognize that this is a P-pod deployer. Look, there are CubeSats that are compressed inside, and there's the spring compressed. The CubeSat, all the CubeSats need to withstand a force of 1320 newtons across all load points. This is an instance in which the launch handling is imparting a load. Across all of these CubeSats, they should be uniformly experiencing 1320 newtons. Just by the way that this is set up, the steady state is that all of these should be uniformly experiencing the same load from this endpoint to this endpoint. That's why all of these CubeSats need to withstand that amount of load at least. And that answers the question, what if one CubeSat doesn't handle the load? If one CubeSat can't handle the load, what you would observe is that one of the CubeSats would crunch. But it looks pretty good here, so I think it's safe to say that all of these CubeSats can. For our CubeSat, this load was analyzed with a software called Onshape, which you all should have downloaded over the weekend. So you'll go through the process of actually analyzing load during the semester, which is really exciting. Okay, so that's one kind of load, compressive load. But here, this large spacecraft, while it's in the rocket fairing in this orientation, has to withstand the load of gravity of all the components in this configuration for a while, up until it gets to the launch pad. And then while it's launching, it's also going to feel that acceleration in that same direction as gravity. These spacecraft down here, if they're mounted to a shear wall like this, they're going to experience a shear force due to gravity pushing that face down. That's not something that the spacecraft would experience in space. It's something distinct to the way that it is mounted to that ESPA ring. So that's also something you have to take into consideration for structural integrity. That's not necessarily part of the mission. All right, let's get to some good stuff. This source of load, launch, is probably going to be the driving critical load. We were talking earlier about vibration, and this is what a launch, or like a typical vibration spectrum of a launch looks like. The spacecraft on board really gets shaken up. Not only do they get shaken up, but there is a lot of acceleration that the spacecraft experience. Acceleration translates into loads. In this case, there's a dynamic load where there's a certain amount of acceleration that is changing over time and peaks at about almost 4 Gs. So you got to make sure that your spacecraft interface with the rocket can withstand those kind of loads. There are also loads associated with changing thermal environments. There's something called a coefficient of thermal expansion, where you have this beam given some temperature rise, so it gets hotter, there's going to be some delta in the length of the bar. But say that your bar or your beam is constrained on both sides by a wall. That difference in length is not possible, so instead you get a compressive force. So this is what a stress profile looks like for a sample that is experiencing a lot of temperature change. You'll see that higher temperatures give way to higher stresses. So you want to make sure that during your entire mission, your entire thermal profile, that you think about the most extreme thermal environments you're going to experience, and make sure that your components that are have boundary conditions within your structure are going to survive that kind of thermal load. Oh gosh, okay, and then there are other sources of load like pressure. There's something called max Q, where the atmosphere, as an object is going through the atmosphere at some certain velocity, you're going to compress this air front to the point where a shock wave happens. When that shock wave happens, that's called the max Q point, and here you can see a visual depiction of it. Our spacecraft are going to be within the rocket fairing, so we don't necessarily need to consider this, but the space shuttle, for example, did. Other sources of load that we aren't going to experience, but other spacecraft do, are pressurized tanks. We're short on time, so I'm going to skip it. And other sources of loads are mechanisms. This is a sail that is unfurling. Sails are very, very delicate, so here was some modeling of, as the origami is unfolding, what are the high stress points? Is the sail going to tear? For articulated solar panels, these little joints experience dynamic loads due to the angular momentum and linear momentum that this large mass has. But this little mechanism needs to decelerate, so that's a source of load for this component. Okay, and I'm going to finish off the lecture with materials. Most structures have an associated material associated with it, but the materials, depending on their material properties, can drive, say, the mass of the system. So material properties are like density, stiffness, strength, ductility, coefficient of thermal expansion, thermal conductivity, fatigue, outgassing, and cost. And the way that these properties affect the spacecraft are, these are strength and stiffness. Those associate with the way a spacecraft can handle the critical load. Same with the coefficient of thermal expansion. That also affects what critical load is going to cause the spacecraft to fail. We were talking about thermal conductivity in the way that heat is distributed. Fatigue is for cyclic loads, for components that are experiencing loads between a minimum and a maximum over time and it cycles. That cycle can cause something called fatigue, which can fail components. That can limit your mission lifetime. Some components, given their molecular composition, can outgas, which is kind of like transmitting molecules because there's a vacuum around. This affects the way that we adhere to the GEVs, so the environmental standards. And different materials cost different things. So let's look at this table of common materials. The most common materials are aluminum, steel, titanium, and then up and coming is a carbon-carbon composite. Aluminum is by far the most common material in spacecraft, but let's look at why. So aluminum is very light. It's not as light as carbon-carbon, but it is the lightest of these metals. It is quite strong. Most of the time it's strong enough. It's ductile. And I think the thing that makes it most attractive, it is thermally conductive, but the cost is just magnitudes less than stainless steel or titanium. Stainless steel is maybe 2 to 3 times more heavy. So that's a mass design driver that makes people not want to choose it. although it is very, very strong compared to aluminum. For really special cases, aerospace engineers will use titanium, which is very, very expensive, but has the strongest, it's the strongest material. For super light and thermally sensitive applications, we can use carbon-carbon. Okay, oh my gosh, only 5 minutes left. The last design driver is process. You just want to make sure, pretty much, if you can build it, then it's a feasible design. If you can't build it, then you should rethink the way that you're designing it. This is Artemis's mechanical integration slides. So when you're designing your spacecraft, think about how you're going to assemble it. If it turns out that you can't think of a way to assemble it, then the design is not feasible. You want to go all the way from step 0, which is having all of your components disassembled, to a full spacecraft.